start with the first law of thermodynamics. First law of thermodynamics is a very intuitive physical law, which is nothing but the law of conservation of energy. We will try to get into the details of the first law of thermodynamics to the extent that we desire, but we will start with something which is very intuitive, and that intuitive is like how to write the energy balance for a control mass system. So, let us say that there is a control mass system, some energy is transferred to it, some energy leaves from it, and then the remaining energy, so some energy is coming into it, some energy is going out of it, so whatever energy is getting in and whatever energy is going out, we can say that energy in minus energy out is equal to, or the rate of energy in minus the rate of energy out is nothing but the rate of change of energy of the system itself, right. So, here we are making one assumption that within the system everywhere the energy is the same, right, that locally the energy, specific energy, here is something, here it is something, here it is something, it is just like considered as a lumped mass, where we are writing the total energy E. So, this total energy is distributed, I mean it may be unevenly distributed also, that does not matter. What matters is that this is like a lumped body which has a total energy E. Because it is a lumped body, how it is distributed inside it does not matter. So, it is a unique value E for the system, okay. And then therefore, this E is a function of time only and not a function of position. That means in terms of these properties per unit mass, that property is uniformly distributed within the system. So, this is a very intuitive physical law, and I will try to give an analogy or draw an analogy of this with, say, instead of energy balance, let us talk about money balance. So, let us say that this is a bank account. So, somebody has deposited some money in the bank, and then the same person has after some time withdrawn some money. So, when the money comes in and when the money comes out, whatever is the rate at which the bank balance changes in the difference between these two, you might argue that the bank can give some interest, right, and that interest sometimes is written in terms of energy generated, right. So, energy generated is like the money generated out of the interest. So, some money has been deposited in the bank account, some money has been withdrawn, but you see that in your bank account the net change is a little bit more than the difference between these two, and that is because the bank is giving you some interest. Now, let us try to apply this for a system where the interaction is only heat transfer and work done. So, example, apply to the following case. Number 1, energy interaction only by means of Q and W, heat transfer and work done, and the process is a cyclic process. Okay. So, if the energy interaction is by means of only heat and work, so energy interaction only by means of heat and work, interaction means interaction with what? So, interaction, the system interacts with only the surroundings, right, energy interaction with the surroundings, that we must specify only by means of heat and work, and that means there is no energy generation, only the system is interacting with the surroundings through heat transfer and work done. So, this is 0. Heat transfer, so net in minus out, energy transfer by heat, we say Q dot, the rate of energy transferred by heat. If it is transferred to the system, it is positive, right, as per our sign convention developed. So, we write this as positive, and work done, if work flows out of the system, it is positive. Therefore, it comes with the out, the net positive heat transfer comes with in, net positive work transfer comes with out as per our sign convention, and this must be 0 for a cyclic process. This is very important. Right? Why? For a cyclic process, the system comes back to its original state, because that is the definition of a cyclic process. What is the definition of a cyclic process? You start with a state point, you go through a sequence of points and then sequence of state points, and then you come back to the same state point. So, once you come back to the same state point, there is no net change of the energy of the system, right. So, this is equal to 0. So, this is in terms of the rate process. So, if you are considering the total heat transfer and total work done, you can write cyclic integral of heat is equal to cyclic integral of work. If you now find out the total heat transfer and total work done, that is integrate this over the cycle and over time. Okay. So, physically what does it mean? Physically it means that if you transfer some heat to the system holds the capacity to do an equivalent amount of work. Historically, when Joule did his experiment, which all of you have perhaps learnt in your school, high school, then the units of heat and work used to be different, and then heat unit was used as calorie and work unit was used as joule. So, to account for the mismatch of the heat unit and the work unit, a mechanical equivalent of heat was a conversion factor that was used to relate these two. However, in SI unit the heat and work both are in the unit of joule. So, therefore, no conversion factor is required. So, this you can say is a statement of first law of thermodynamics, which is nothing but an accounting of energy balance, which I have already told that first law of thermodynamics for a cyclic process undergone by a system. For a control mass system undergoing a cyclic process. But you know, this may be a very initial point to start our discussion, but in reality the processes that are taking place are not cyclic process always. So, to understand that how we can write the first law of thermodynamics for any general process, for a control mass system, we will try to advance a little bit from the cyclic process. For any process undertaken by a control mass system. Now, we assume that there is some plane, let us say PV diagram as an example, it could be any two independent properties. We consider a process, cyclic process having two constituent processes. So, we start with 1 and go to 2 via path A and come from 2 to 1 via path B. We consider another cyclic process between the same state points where we go from 1 to 2 via path A, but come back from 2 to 1 via path C. Okay. So, now we can write for the process A plus B cyclic integral of del q is equal to cyclic integral of del w. I have already told you in one of the previous lectures that why these are not dq and dw, because these are path dependent functions and these are called as cyclic integrals, that means integral over the entire cyclic process, or in mathematical terms these are called as contour integral, integral over a closed contour. So, 1 to 2 by path A plus 2 to 1 by path B is same as 1 to 2 del W by path A plus 2 to 1 del W by path B. Similarly, 1 to 2 del Q plus 2 to 1 now by path C this is the other cycle is equal to 1 to 2 by path A plus 2 to 1 by path C. Okay. Okay. So, now let us say this is equation number 1, this is equation number 2. You subtract one from the other, subtract 2 from 1. If you subtract equation 2 from equation 1, so you can write very interestingly, although del Q and del W individually are path dependent, we see that the difference of del Q and del W, that is del Q minus del W, this its integral from 1 to 2 does not depend on whether the path is B or C, and these paths B and C are absolutely arbitrary. That means integral of del Q minus del W is path independent so long as the end states are identical. So, if that be the case, then you can write del Q minus del W as the exact differential of a property. This property is called as energy of the system. So, whatever terminology as energy we intuitively started with to discuss about the first law for the cyclic process, that energy is now defined in terms of the difference of work and heat transfer. So, this E, this is defined as energy of the system. So, why this is dE and not delta E? The reason is that when you integrate this, if you write integral of dE, that is E1 minus E2, right, and that is the correct thing, because the difference of or the integral dE from 1 to 2, that is E1 minus E2, is something that does not depend on whether from 1 to 2 you went by path B or by path C. Okay. So, that is why it is D and not delta. So, when you write D of something, this is called as exact differential. So, let me write down these terminologies. This is inexact differential, this is exact differential. So, the function which comes with an inexact differential is called as path function, whereas the function that comes with exact differential is called as point function or property. So, this and these are path functions, and this is called as point function or property. Why it is a property? Because the change in property does not depend on the path, it only depends on the end state points. So, with this understanding, let us go a little bit deep into the statement of the first law of thermodynamics for a control mass system for any process. So, we will rewrite the equation. So, we can write so physically what does it mean? If you transfer some heat to the system, it may use some of the heat to do work and the remaining heat will actually be used to increase the energy of the system. Okay. So, this E now, what is this? This E is considered to be kinetic energy, that is half m, maybe let us write half m c square. I am not writing half m v square because v in thermodynamics we already use for volume. So, this is actually that half m v square. This is potential energy, and any form of energy which is other than the kinetic and potential energy, this is called as internal energy. So, we come up with a new property called as internal energy. So, the potential energy depends on the reference state. Similarly, the internal energy also depends on the reference state. Potential energy, why does it depend on the reference? So, potential energy is mg into the height with respect to the datum. So, the with respect to the datum, whatever is the height, based on that the potential energy is calculated. Internal energy is also calculated based on a reference. So, sometimes in the thermodynamic property table, in addition to in addition to pressure, volume, temperature data, you will see additional properties. So, this is the first additional property that we learned from the thermodynamics, first law of thermodynamics, that is specific internal energy this is small u. So, all the energies or all the parameters, the total is capital letter or uppercase, the total per unit mass is small letter or uppercase, that is called as specific. Okay. So, this specific internal energy is tabulated along with pressure, volume and temperature data in the table, and you will see that this may be necessary for working out problems related to the first law of thermodynamics. So, physically what is the origin of this? This is essentially intermolecular form of energy. So, kinetic and potential energies are macroscopic manifestations of the mechanical energy. But other than that, there are several intermolecular forms of energy due to molecular configuration, and all these things essentially sum up with it in the form of internal energy. So, from classical thermodynamics or macroscopic thermodynamics point of view, which we are studying in this particular course, in the classical thermodynamics perspective, the internal energy is any form of energy which is other than kinetic and potential energy. That is how it is defined. Instead of getting into its detailed intermolecular picture, which a course on physics will provide, here we are considering that this is a form of energy which can be attributed due to the intermolecular form of energy. So, now interestingly, in many thermodynamic processes, the changes in kinetic energy and potential energy are negligible as compared to other effects. So, in that case dE will be approximately equal to du. So, then this will lead to this is the form of the first law that most of you are familiar from your school level. Now, when you are asked to describe the assumptions behind this equation, sometimes students make mistake by saying neglecting kinetic energy and potential energy. The fact is that it is not kinetic energy and potential energy, those are negligible as such. It is the change in kinetic energy and potential energy that is negligible as compared to other forms of energy. So, today we have learned the following. We have started with a basic physical law concerning energy balance, and from the basic physical law concerning energy balance we came up with a description that connects the heat transfer and work done in a cyclic process, and that we described as the first law of thermodynamics for a cyclic process. Therefore, the first law is nothing but an expression for energy balance expressed in terms of heat transfer and work done. So, then we extended that to the first law of thermodynamics for a control mass system for any process, and that boiled down to this form, and then for special cases when kinetic energy and potential energy is negligible, changes in kinetic energy and potential energy are negligible, this is the form of the first law for a control mass system undergoing any process that we came up with. In this process we have come across a new property called as internal energy. Please try to look into the thermodynamic tables that you might have in your textbook, and let me see whether in this computer file I have some, yes, so yes. So, I will show you in the screen that you can see that just like specific volume, temperature, pressure, you have a last column which is the internal energy in this table. So, just like you have Vf, Vg, Vfg, similarly you have Uf, Ug, Ufg. So, just like pressure, volume, temperature, you can consider internal energy also as a property, and you can take that property from the table, property table, just like as you take the property of pressure, volume or temperature from the property table tabulated in the books. So, with this little bit of introduction on first law for a control mass system and introduction to internal energy as a property. We stop here today and we will continue in the next lecture.